Today, let's talk about how to use trigonometric substitutions to evaluate definite integrals. According to the Fundamental Theorem of Calculus, we know if the capital Earth is an antiderivative of the little earth, then the definite integral from A to B, little earth x dx is equal to capital Earth of B minus capital Earth of A. So you see, the key step for evaluating a definite integral is to find an antiderivative of the integrand. In order to do that, we need to make the integrand as simple as possible. For example, if the integrand contains square root of a squared minus x squared, then we can do a substitution. X equals a sine theta, and theta is between 0 and half pi. So let's plug in. So get a squared minus a squared sine theta squared. And we take a squared out. So a squared times 1 minus sine theta squared, which is cosine theta squared. Because theta is between 0 and half pi, we know cosine theta is non-negative, so we get a times cosine theta. So in this way, we eliminate the square root. Similarly, if it contains square root of a squared plus x squared, then we can do the substitution x equals a times tan theta. The reason is because we can use the identity tan theta squared plus 1 equals secant theta squared. Using that, we can again eliminate the square root. If it contains square root of x squared minus a squared, then the substitution would be x equals a secant theta. Again, the reason is this identity. Now let's look at two examples. The first one, I equals integral from 0 to 2 dx over square root of 4 plus x squared. We can use the second one. Okay, so let x equals 2 tan theta. Then we know dx equals derivative of 2 tan theta x equals 2 secant theta squared d theta. And we also need to change the limit. So when x equals 0, that means tan theta equals 0. So theta equals 0. If x equals 2, so 2 equals 2 tan theta. So we know tan theta equals 1. So theta equals pi over 4. So the given definite integral can be written as I equals 0 to 0, and then 2 corresponding to pi over 4. So now dx equals 2 secant theta squared d theta. The bottom square root of 4 plus x squared now becomes 4 tan theta squared. 0 to pi over 4, and then 2 secant data squared d data, and the bottom part 4, and then 1 plus 10 data squared. So x equals secant data squared. Let's continue. So we get 0 pi over 4. The top still 2 secant data squared d data. But the bottom, we get 2 secant data. We can cancel one factor, 2 secant data from top and bottom. So we get 0 to pi over 4. So secant data over 1 d data. In order to evaluate this one, both part, top and bottom, multiply by 10 data plus secant data. So we get 0 pi over 4. And then the bottom, so we get 10 data plus secant data. The top, secant times 10, so secant data times 10 data plus secant times secant, so secant data squared d data. So 0 to pi over 4, and then still have the same bottom, 10 data plus secant data. But the top, you see, this part actually is the derivative of secant data. And the second part is actually the derivative 10 data, and then d data. So you can see we can write the top as what? As d secant data plus 10 data. For the bottom, I change the order, so write secant first plus 10 data. At this point, we can use this formula, the integral du over u equals ln absolute value of u plus c. So if we review sin data plus 10 data equals u, then we get ln absolute value secant data plus 10 data. And then evaluate at pi over 4 minus the value at data equals 0. We can plug it, so we get here ln when data equals pi over 4, so we get secant pi over 4 equals 1 over cosine pi over 4, which is square root of 2 over 2 plus 10 pi over 4 equals 1. When data equals 0, so we get ln secant 0 x equals 1 over cosine 0, which is 1, plus 10 0 just equals 0. So you can see the final answer should be ln. Here, x will get square root of 2. The second part equals 1. And ln 1 just equals 0. So that should be the final answer. Now, let's look at the other example. Which one is actually pretty interesting. So I equals integral from 0 to 1. 1 minus x squared over x plus square root of 1 minus x squared dx. We do the substitution. X equals sin data. Then we know dx equals the root sin x equals cosine data times d data. So then I equals when x equals 0, we know data equals 0. When x equals 1, sin Theta equals half pi because sine half pi equals 1. So half pi, the top now becomes 1 minus sine theta squared. And d theta is cosine theta d theta. The bottom, sine theta plus square root of 1 minus sine theta squared. 0 to pi over 2. The top, 1 minus sine theta squared equals cosine theta squared times cosine theta. So equals cosine theta cubed d theta. The bottom, sine theta plus 1 minus sine theta squared equals cosine theta squared. Take square root, so we get cosine theta. At this point, you can see it is hard to integrate because we have a bottom here. In order to eliminate the bottom, we can use this formula. A cubed plus B cubed equals A plus B times A squared minus AB plus B squared. So if we can create some part, say sine cube plus cosine cube, then we can cancel the bottom. But how can we change sine cube, cosine cube? How can we change cosine theta to sine theta? We know cosine half pi minus variable u. We know we get sine u. Using this one, we can change that to sine. So I equals, so we do a substitution. Theta equals half pi minus u. So start from this one. Then when theta equals 0, u equals half pi. When theta equals half pi, u equals 0. And we already know cosine theta equals cosine half pi minus u, which equals sine u. So we get sine u cubed. And d theta equals, you can see the root here equals negative, so equals negative du. But the bottom, let's see, so we already know sine theta equals cosine u plus cosine theta equals sine u. Now we flip the upper limit and the lower limit, so we get 0 to half pi. Here should put negative, but here we already have negative, so cancel out. So then we get sine u cubed over sine u plus cosine u du. We know the variable in a definite integral, just a dummy variable, you can change it to any other variable. So why not change back to theta? So then we get 0 to half pi. So here we get sine theta cubed over sine theta plus cosine theta d theta. Then we get two expressions for I. One is here, one is here. So then we express I equals half I plus I. For the first I, we take this one. So for the second I, we take this one, and then we combine them together. So actually we get 0 to half pi. Because they have the same denominator, we can simply add the top. So we get sine theta cubed plus cosine theta cubed d theta, and the bottom sine theta plus cosine theta Now we can use these formulas. So we get 0 to pi over 2. The top now becomes sin theta plus cosine theta. And then multiply by sin theta squared minus sin theta times cosine theta plus cosine theta squared times d theta. And the bottom, sin theta plus cosine theta. So we can cancel this factor. So we get integral from 0 to half pi. And at the same time, we can simplify the integrand. Sin squared plus cosine squared x equals 1 minus sin theta times cosine theta equals half sin 2 theta d theta. We know the antiderivative of 1, x is theta. The antiderivative of this one, x equals to negative, now becomes positive. Cosine 2 theta over 4. And then we evaluate at pi over 4 and 0. So let's plug in theta equals half pi. So we half pi. Oh, don't miss a half. Sorry. And here we have half. And here we have half. Okay, yeah. So then we get half. Let's plug in theta equals half pi. So we get pi over 2 plus sin pi equals negative 1. So negative 1 over 4 minus then theta equals 0. 0 plus cosine 0 equals 1 over 4. So we get half pi, negative 1 over 4 minus 1 over 4. So we got negative 1 over 2. Finally, we get finally we get pi minus 1 over 4. That is the final answer.